Welcome back. In previous videos, we've dealt with a lot of the major mysteries of our universe, like the Big Bang and dark matter. But now it's time to deal with the biggest mystery of all. It's the one we call dark energy. It makes up about 68% of the universe, but no one's sure what it is or where it comes from. We know it's there because we've recently discovered its surprising effects that we can observe and measure, and a theory has been proposed to account for it that answers some questions. But it doesn't tell us where it came from, and it results in predicting that the entire universe will blow up in just a few billion years. In this video, I'm going to propose a different explanation for dark energy that's simple and obvious, and also leads to predicting a longer life and a calmer end for the fate of our universe. But let's begin by discussing what we know about the effect dark energy has on the universe and how we know it's there. We'll talk about the benchmark model, which is the current view of how it works, but it doesn't have much to say about where the energy comes from or how it's created. Then we'll introduce the propositions of black marble theory, which will suggest new ideas and provide a very different description of the way our universe is going to end. Well, let's start by reviewing a short history of what cosmologists have had to say about energy in the universe. It was about a century ago that Albert Einstein developed his general theory of relativity that explained how matter contracts space to produce gravity. The universe he described had a small problem. His equations predicted that unless it was expanding or contracting, it would be very unstable. Now, most of the other astronomers of the time believed that it was a static universe, and in order to make his equations produce a stable universe, he added a term he called lambda, which stood for the cosmological constant, a force that made him a bit nervous because he couldn't explain where it came from. Well, a few years later, Edwin Hubble, working with some other astronomers, made some startling observations that changed the study of cosmology forever. He discovered that the strange objects called spiral nebula were actually collections of billions of stars, galaxies far away from our own Milky Way. By using data collected by other astronomers, he was able to determine that the light from the galaxies was shifted toward the red end of the spectrum, which meant that they were all receding away from us. Moreover, the speed of their recession increased as they got further away. Hubble had discovered that the universe was expanding. He observed that the speed of recession of a galaxy increases in direct proportion to its distance. If it was twice as far away, it receded 2 times faster, and so on. Well, this relationship is known as Hubble's law, and once it was refined, it enabled us to determine the vast distances of far galaxies by measuring the redshift of their light. Well, when Einstein learned about the expansion, he saw that he could have predicted it if he hadn't added the cosmological constant lambda to his equation for general relativity, and according to legend, he called this his biggest blunder. Well, now that we knew the universe was expanding, it was possible to run the movie backwards and deduce that all of the universe's contents must have started from a single location and begun with an immense primordial explosion. An astronomer named Fred Hoyle didn't believe the theory, and he ridiculed it with the name the Big Bang. Well, the name stuck, and after a few false starts, it was developed into the well-accepted Big Bang theory that we have today. And the theory postulates that all of the matter and energy that makes our universe was created in this beginning event, and as it cooled and dissipated over time, the gravity of the matter would slow down the expansion. Now, this slowing down was assumed to occur at a steady pace, and its rate was given the name of Hubble's constant. Now, through most of the 20th century, the focus of cosmology centered on predicting the evolution of the universe by refining the value of the Hubble constant. There were three possibilities for the eventual end of the universe. It depended on how much negative energy, or gravity, was produced by the matter content. Now, if there was not enough matter to stop the expansion of the universe would expand forever until all the galaxies became so distant from each other that nothing could be seen outside of our own. This version is shown by the red line in this visual, and it was called the Big Chill. The blue line shows what would happen if there were enough matter to stop and then reverse the expansion. Gravity would pull the universe back into a single point, and they call this scenario the Big Crunch. And the third possibility was that there was just enough matter to slow the expansion, but never to reverse it, and this was called the flat universe, as shown by the green line. Now, most observation in the space near to us indicated that the universe was indeed flat, or nearly so. But as the 20th century drew to a close, a new discovery was made that once again turned astronomy on its ear. In 1998, a group of astronomers announced that they'd been looking at supernovae in space much further than Hubble was able to see, and they discovered that the rate of expansion of the universe had been increasing for the last 5 billion years. Well, this was truly astounding, and it brought up a major problem. In order for the expansion to happen, there had to be a new energy to cause it. The question was, what was the source of this energy? Well, the answer they came up with was that it was called dark energy, which was just another way of saying that they had no idea. The current theory about dark energy is called the benchmark model, or the lambda CDM model. CDM stands for cold dark matter. It's cold because it's inert and it doesn't interact with ordinary matter. And they don't know what it is, but basically it's the same stuff that we described in the previous section called black dust. Now, the lambda component has been resurrected from the term that Einstein discarded from his general theory equations, the cosmological constant. Now, he used it to represent an unknown kind of energy, and now it's been appropriated to represent dark energy in the revised equations. But like Einstein, however, the proponents don't really know what it is or where it comes from. Now, the theory is based on the premise that dark energy is an inherent property of space itself. It imparts an energy pressure that remains constant as space expands. So the more space you have in the universe as it expands, the more dark energy it contains. As the universe expands from the Big Bang explosion, the matter is dissipated and its gravitational effect gets smaller. So the rate of expansion slows down as time goes on. Before the acceleration was discovered, cosmologists expected it to continue slowing down throughout the life of the universe. But in 1998, that all changed. It was discovered that the universe had indeed slowed its expansion for the first 9 billion years as expected, but that it had been accelerating for the last 5 billion years. Now, cosmologists needed a new source of energy to explain this, so they resurrected the cosmological constant, lambda, in their equations and came up with the idea of dark energy. This slide shows how it works. Dark energy is proposed to be an inherent component of space. And so, as space expands, dark energy grows, as shown by the dashed blue line. The matter energy remains dominant for the first 9 billion years, so the expansion rate slows down, as expected. However, 5 billion years ago, the matter energy fell below the growing dark energy and the expansion began to accelerate. Now, the result of this scenario is that dark energy will continue to accumulate, propelling more expansion of space in an exponential growth that will eventually tear the fabric of space apart, whatever that means. Cosmologists call this event the Big Rip and predict it to occur about 20 billion years or so from now. Well, frankly, I wish we'd come to a kinder, gentler end, and the second basic idea of black marble theory, called bright energy, can do just that. The only way we know to get new energy in the universe is to release E energy. We can get a little by releasing stored binding energy, but we can get a whole lot more from nuclear reactions. And the place to look for nuclear reactions is the night sky. Every star we see is a furnace of nuclear reactions pouring energy out into the universe, and it might be a good place to look for a better explanation of dark energy. In the video segment about energy, we described how explosions release their energy. We noted that a portion of the energy is released as radiation in the form of heat and light. In the explosion we call the Big Bang, the radiation was quite powerful, and it propelled the expansion of the new universe for the first 50,000 years. It quickly dropped to a negligible level, however, and the second major component of explosions that I call expansion energy took over. This energy created the space and imparted the initial kinetic energy that expanded the new universe. And the gravity of the leftover matter began to slow down the rate of expansion. So this set up the behavior of the universe that cosmologists believed would exist to the end of time until 1998. But when acceleration was discovered, the need for new energy became apparent. Now, it's the premise of black marble theory that the biggest source of expansion energy in the universe today comes from the nuclear reactions occurring in stars. They're converting ordinary matter to energy via E equals mc squared at a prodigious rate. Our sun, which is a pretty average star, is converting about 400 tons of hydrogen to 380 septillion joules of energy every second. Now, there's about a septillion of stars of various sizes in the observable universe. They're doing the same thing. The observable universe is likely only a fraction of the total universe. Now, add to that the immense energy contributed by frequent supernovas, and there should be plenty of energy to propel an accelerating expansion rate. And because the source of the energy is coming mostly from stars and supernova, I've dropped the term dark energy, and instead I call it bright energy. When we look at the night sky, we only see a small portion of bright energy. We call it starlight, and it only contains the small radiation portion of the nuclear explosions in the stars. We can't see the expansion energy, that's why it's called dark energy. But this component is what's propelling the acceleration of the expanding universe. Now, this slide shows how it would work. There's no dark energy as an inherent component of space, but there is a substantial element of bright energy that comes mostly from stars and supernova. This energy first appears about 400 million years after the Big Bang, when the first stars began to ignite. It grows rapidly at first and then settles down as fewer stars are created because the hydrogen gas they're made of is getting used up. Today, stars are being created at about 1/30th of the rate they were during the peak period in the early universe. As in the dark energy scenario, matter energy dominated the universe for the first 9 billion years. Well, as the expansion dissipated the matter, about 5 billion years ago, its energy fell below the level of bright energy, and the expansion rate accelerated, just as in the dark energy scenario. Unlike that scenario, however, the acceleration does not continue forever. As the supply of ordinary matter is depleted, star formation slows and then it stops altogether. And the bright energy will disappear from the universe. The acceleration will end and the universe will resume its slow expansion toward its eventual end. So the bright energy theory explains our observations equally as well as the dark energy approach, but it predicts a much more gentle and, I think, a more satisfying end to the universe. And it also casts a new light on the role of ordinary matter in the universe. If new energy in the universe comes from bright energy, it follows that the source of the energy comes from the conversion of ordinary matter. So ordinary matter is the fuel for the energy that we need and the universe needs for its operation. And this fuel has a limited supply. Ordinary matter was created at the time of the Big Bang, and when it was created, that's all there was. There's no process that we know of that will create more. So if the universe is using this fixed supply to meet its energy needs, it's clear that it can't last forever. And therefore, we can come to the following remarkable conclusion: that the universe creates new energy by converting its supply of ordinary matter to energy, and when the supply is exhausted, the universe will cease to evolve, and the expansion will slow to a halt. There's one more corollary to the bright energy proposition, and this may be the most important point of all. It concerns the law of conservation of energy. Now, that fundamental law states that the energy may be neither created nor destroyed except by conversion of matter via equals mc squared. Now, the elephant in the room for the dark energy theory is that it violates the law. Since dark energy is an inherent part of space, it just appears whenever the space expands. Most cosmologists know that dark energy exists, so they tend to overlook this problem and assume it will be solved somehow in the future. And some attempts have been made to explain it, but generally it's treated as one of the science's many unsolved mysteries. Well, black marble theory proposes, on the other hand, that bright energy is created from the conversion of ordinary matter, and that both sides of the E equals mc squared equation remain equal. So the law of conservation of energy remains in place. Well, this point alone provides a powerful argument that bright energy is a more plausible way to explain the acceleration of the universe. Of course, all good things must come to an end, but somehow I like this end better than the big rip suggested by the benchmark model. So at this point, we've covered many of the questions about our universe with explanations that are somewhat original, but hopefully build up logically from the basic premise that matter can exist in a new state containing no space called black matter. There's another question that's plagued scientists for many years. They've tried to define gravity as a fundamental force of nature, and they're attempting to integrate it with the other three forces. So far, nobody's been able to do it. Well, it turns out that black marble theory can shed some light on this quandary. And in our last section to follow, we'll turn our attention to universal gravity. Thanks for watching.